Hello, everybody. Today's presentation will be on fraud detection for our deep learning project. Financial institutions, commercial banks, online service providers face a constant challenge identifying fraudulent credit card transactions from millions of legitimate ones. So in our project, we're going to be applying unsupervised deep learning methods to see if we can outperform a traditional baseline model using key metrics, precision, recall, and AUC ROC. Our motivation for using unsupervised learning methods is due to the model being more versatile across different platforms and the understanding that labeled data may appear normal, non-fraudulent. However, as new fraud cases appear over time, how we define fraud may change.
The dataset is from a Kaggle competition hosted by IEEE's Computational Intelligence Society. It is a large dataset of credit card transactions with almost 600,000 entries or rows and almost 400 features or columns. This data is challenging in that the vast majority of features are unknown or proprietary, meaning that we do not know what they represent. There are also significant missing values or NaNs in the dataset, with many columns having more than 86% missing values. We use principal component analysis to look for highly correlated, thus redundant features, allowing us to later drop those features. Lowering the number of features helps reduce the risk of overfitting. Lastly, the dataset is split 60-20-20 into a training, validation, and test set.
We ran a variety of simple unsupervised clustering models as our baseline and chose two to look at in more depth. The first was an isolation forest, which is a tree-based anomaly detection algorithm. It ran in under 12 seconds, however, it had unsatisfactory precision and recall at every threshold. The second was a Gaussian mixture model, which is an unsupervised clustering algorithm that uses a Gaussian kernel instead of a distance kernel. We saw improved performance with this model and ultimately chose to use it as our baseline. The AUC ROC was 0.773. We computed precision and recall at a high contamination level of 30% to heavily bias towards type 1 errors because it's important to consumers and financial institutions to identify as many potential fraud cases as possible. Then an auditing process can be used to weed out false positives. This gave us a precision of 0.295 and a recall of 0.702.
For the deep learning model, we chose to train an autoencoder. It is a neural network consisting of an encoder which maps an input vector x with 368 features into a lower dimensional space called the latent space, and a decoder which maps this vector in latent space to x star back in the input space. We train the autoencoder by minimizing the mean squared error between x and x star. As shown in this figure, we're using 3 linear layers with ReLU and dropout layers in between for the encoder and a symmetrical structure for the decoder. Since the vast majority of the training data is non-fraudulent, it is expected that the fraudulent data would have a higher reconstruction error when fed into the autoencoder. We then use a threshold on the reconstruction error to flag which transactions are fraudulent.
After the autoencoder, we add a post-processing step that uses user ID to help determine fraud. Essentially, card info alone is not sufficient to determine users, as many users can be associated with one card. Some of these users may or may not be fraudulent. We use multiple variables such as geographical location in addition to card info to determine users. This is essentially a clustering step which allows for the characterization of aggregate behavior in addition to single transactions.
First, we train a model to detect the anomalies on individual transactions. Then we gather the transactions per UID. Then thirdly, we classify these UIDs using two different methods. In the first method called the average rule, we obtain the UID reconstruction error by averaging over all the reconstruction errors of the individual transactions in a specific UID. In the second method termed the fraction rule, we use a threshold to classify which transactions are fraud and then compute the fraction of fraud transactions per UID. If a majority of transactions are fraud, we consider the whole UID as fraud. Next slide. Our performance metrics are as follows. Our train time is about 12 to 15 minutes for 100 epochs. Using the average rule, we achieved an AUC of 0.803, a recall of 0.719, and a precision of 0.346. Using the fraction rule, we have an AUC of 0.738, a recall of 0.720, and a precision of 0.341. Higher precision implies fewer false alarms, less customer friction, and fewer wasted manual reviews. Higher recall implies more fraud dollars prevented, lower chargeback issues. So we see that autoencoders with UID-based fraud detection beat baseline models on all performance metrics, thus achieving the goal of our project.